Welcome to anyone watching. In this video we're looking at the engine instruments as a cluster which I've built for my Simpit, and that's through Digital Combat Simulator. This was initially interfaced with each stepper motor having its own USB connection on individual COM ports over IRQ serial using DCS BIOS. But then I've adapted it then to run on an RS487 Arduino network. To take a look at the instruments, I'll do a very quick startup of the engines. Battery, inverter, APU power, AC gen left and right, boost pumps. So this will be a startup of the APU and then the left engine followed by the right. I'll just zoom in on the engine instruments, and then if I superimpose two images, one of the physical panel builds and another of the throttle. I definitely give DCS 10 out of 10 for the sound effects. I'll just lower the engine volume a little. At 100% APU RPM, we'll crank up the left engine. And I'm going to wait now till that stabilises at about 60% RPM before I crank up the right engine. For my Simpit, my main focus was to now work on the right console and then do the front dash last. But before getting to the right console, I really did want to have a look at some of the gauges and how it would work to implement them. So we've stabilised around 60% now, so we can advance the right throttle. There's a lot to the engine instruments, so I've simplified it in my design that whereas there are actually a total of 16 gauges, because the temperature and RPM gauges, they have a sub gauge within each, I've left those out, as well as the flags that you have within the temperature gauges. So this has made my first attempt at building this more straightforward. One of the other small details which I may add a little bit later on is coloured bezels around each of the gauges, just to give the front just that finish. So we both have the engine stabilised, we can shut down the APU. So if I advance the throttle a couple of times, and we can see that update within the sim and on the physical panel. At this point, if I flip the inverter switch on the electric panel, we can see the impact that has in the sim and on the physical gauges. And then flip that back. So that's a panel for normal use. When flying in night conditions, I wanted to make sure it had the right look. When flying a night mission, I like the lights down, so therefore it's important that the panels are backlit so you can see what's happening. I'm pleased with the look that gives the panel, gives it a good aesthetic, and it's in keeping with what's within the sim. I'll just quickly fire up the APU again so we can see those gauges moving. Another good thing with the simplified design I've used here is that none of the gauges need 360-degree rotation of movement, and also there's no challenges around the speed at which the needles move, unlike some other ones like the altimeter. So at this point we'll take a quick glance at the back of the panel and also where I've interfaced it into my main central hub for my Simpit. For anyone that's looking to build something like this, I've added on extra footage now. It's broken into two parts. So the first part details step by step the build of this panel, and then the second part looks at converting it over to run on an RS487 network. So in part one of the extra footage, we'll look at the construction of the engine panel, and that will be broken into several steps. The first step is to research and choose the components that you will use. So that's thinking about what kind of Arduino, what kind of motor, and what type of H-bridge. And then the second point will be to then, once having chosen your components, to study and test them so you understand exactly how they work. The third point would be to look at planning the wiring of how everything will be connected together. Followed by point 4, which is to understand the Arduino sketches that will be used and what parts need to be modified for your gauge to be configured correctly. The fifth point to then look at the CAD/CAM process to actually start to build some of the key layers of the panel. And then finally, in the sixth part, we'll look at an overview of the different layers that make up the panel. For this panel, I started by choosing my components of the different types of Arduino. So you've got Unos, Nanos, Micros, lots of different ones. I settled on the Nano. Small footprint and lots of input and output points. A very able Arduino. And then do I go stepper or servo route? So in this case I've gone for the steppers. There's quite a few different kinds of stepper out there, so I've gone for the X27 steppers. Let's just get a clear view of that. At the top you've got the lot number from when it's been produced, and then you can see it's the X27 that's the most recent of the 168 series, and then you got the pinouts on the back. You can pick these up online quite easily, particularly from places like eBay or a little bit cheaper on AliExpress. Sitting in between the Arduino and the stepper will be some form of H-bridge. So there's different choices. At the top there you can see in the top left a Adafruit H-bridge, and then in the top right we've got a cheaper alternative, and that's the one I've gone with. It's called an Easy Driver board. I believe it's version 4.4. The component chosen that will sit in between the Arduino and the stepper controls the polarity of the voltage applied to the load. So the order in which it's connected will be the Arduino wired into the H-bridge, wired into the stepper. The next step is to get some time with your components to understand exactly how they work. If the components are quite cheap and you've got a fair few of them, I'd say take one apart and understand exactly how mechanically it works inside, and I'd study the data sheet. So what we're looking at are the innards of the stepper motor from the front. If we also bring up an image of the back of the stepper motor showing the pins, and then to put on screen a key piece of information that shows the pin outputs, and that's the pin outputs in terms of the positive and negatives to each of the coils. In the top left of the screen, the three diagrams of the stepper, the first two on the left show it as a pin designations looking at it from the front of the stepper, and then the third one along on the right shows a pin output as if you're looking at the back of the stepper. This information should help you when you're wiring things up for your first tests. So for the wiring from the Arduino into the Easy Driver board and in turn into the stepper motor, if we first stop to have a look at the schematic for the Easy Driver board. So from the image on screen of the Easy Driver board, there's just a few of the pin inputs and outputs that we're particularly interested in. The Arduino is connected to the three pins at the bottom right of the Easy Driver board. So if you look at the Nano on screen, you can see a black wire which goes from the ground of the Nano into the ground of the Easy Driver board. And then you can see that on the Arduino pins 10 and 11, there's wires that connect into the step input and direction input of the Easy Driver board. We need to provide power to the Easy Driver board, so looking at the top right of the Easy Driver picture, you can see that there's a power in, which it says ranges from 6 to 30 volt. So in this case I've used a 12 volt power supply which is connected at that point. And if you look at the Easy Driver on screen, the physical one I've got there, you can see a black and red wire which will be connected to that supply. What that then brings us to is the connecting of the stepper motor to the motor core outputs of the Easy Driver board. So this is a good time to bring back up on screen the stepper motor pinouts showing which are the positive and negatives for each of the two coils. So if we look at the Easy Driver picture, in the top left you can see pin outputs for motor coil A and B, and if we number those from left to right, 1 to 4, 1 and 2 being for motor coil A and 3 and 4 being for motor coil B. We can see that the back of the stepper motor has pin designations of 1, 2, 3, 4 also. So it would be logical at this point to assume that pins 1 to 4 of the Easy Driver board would connect to pins 1 to 4 in that same order of the stepper motor. But that would not be the case, because if you did it that way, whilst coil A would be energised correctly, the coil B would have the positive and negative the wrong way round at the back of the stepper motor. So the pin designations from the back of the Easy Driver as wired into the stepper would actually be 1 to 1, 2 to 2, 3 to 4 and 4 to 3. And the final thing to bear in mind as you do that is, as you look at the top right image of the stepper motor pinout, of the 3 circular stepper motors it shows, the first 2 are the pin designations as if you were looking at the stepper motor from the front of it, and the one on the right, the third one, is if you're looking at the stepper motor from the rear. So with those main components all wired up, we're at the point now where the code, the Arduino code, has to be correct in order for it to all work properly. So if we have a look at the sketch that I've got on screen here, I've named it G12 for gauge 12 because this is going to be for the APU temperature gauge, which is the 12th one along, and it's connected by USB because at this point each Arduino connected to each gauge will have it be on its own COM port and stream to individually, and it's using IRQ serial. And there's a few little bits of this code we modify to tweak the movement of the pointer to make sure it's within the correct range to be in sync with the sim. And as I've made little modifications, I've renamed them as different versions until I reach the final version that I'm happy is acceptable, that it's pretty much in line with the sim. In this case, that was a 5th version of it. So when we look at the code, you can see that we've got a couple of libraries we include, one of which obviously would be DCS BIOS, the other one being for the stepper. And within the code, we can see a few notes that I've just added in. So I can't take credit for the code itself because I just downloaded it from the ED forums. I can't recall if there's anyone it was from to give credit to specifically, but this code as downloaded, what I'm going to cover now is some of the bits I've tweaked. So the one thing I've noted here is that I'm testing with pin 11 going to the middle of the easy driver, which is step, and 10 going to the direction, which is the right one. So I'm connecting them the right way. The few bits of code here that are important, the first one being this one here, because this information is specific to which of the gauges. So in this case, that's the appropriate code to tell it it's the APU temperature. But if we were to come across here and go to the DCS BIOS website and go to the control reference, let's give that a moment to load. And we're looking at the A10. And what we want are the engine instruments. So the APU temperature gauge was that was a code we had just seen. So let's say if you got this sketch right, but then you wanted to replicate the sketch over and over again for each of the other gauges, you would simply take these snippets of code for the other ones and insert them as needed. So jumping back here, we can see that's what this bit's all about here. In terms of the max speed and acceleration, I've stuck with values of 1,000 on each. The only other bit I've actually altered is the max steps figure, because the greater that figure, the greater the arc of movement, the number of degrees that the pointer on your stepper will move. So according on how you've designed the gauge, you'll need to keep tweaking that figure so that it runs in line with what's happening in the sim. Beyond that, this particular snippet of code here is not actually needed. That's just something that I like. So as I load a sketch and I execute that on the Arduino and I'm streaming to it, I have a very visual way just to see that everything is data-wise streaming through to the nano correctly, but ultimately that will be removed in the final code I use. One final piece of information that's worth noting from within the sketch is this code you can see on screen. There's some annotation around when it's not initialized, when it's zeroed, and when it's running normally. And what all this means effectively in terms of what you'll see is that when the sketch begins, there'll be an initialization sequence where the pointer will move back a number of steps, and what is important is that within that number of steps it must hit the back stop on the stepper motor for it to then ensure it's in the correct position. So now the tests begin, whereby the code can be tweaked to fit each gauge until you have the right code for all the gauges. So here's a picture of the instruments that we're building as taken directly from the DCS manual for the A10C. The main materials that will be used here will be 3mm opal acrylic, 2mm clear acrylic and MDF. Previous videos have covered the process for preparing these and painting these, so I won't recover them now. So I'll jump into Cut 2D, which is a program I've used to make this design. It shows the gauges that I've created here. So there is an option in this program which is to create a circular array, which is a really great way to create all these marker lines precisely. Something that I was aware of is a couple of the gauges within the sim would have a greater range of rotation in degrees than what the stepper could do, so therefore I've altered it on the actual gauges I'll produce, so perhaps that range won't be quite so great, so it won't hit the end stop of the stepper during the time I'm using it. And also, so I can fit all the text in, it's legible. On a couple of them I've slightly tweaked some of what you see letter wise, just so it conveys the same information but it's in a way that can fit within that window. If I jump across now, we can have a look at a 3D preview of how that should look when it's cut on the CNC machine, and that's how it'll look when it's backlit. So if we zoom in, so it'll give a nice finish on that one there. A very quick look now at the machining process, starting with engraving the acrylic with marker lines and text, through to machining of the MDF. Each of the stepper motors will now have wires soldered to the output pins, which will run into a connector. A clear sheet of acrylic will hold all the steppers in place, and this will also allow the backlighting to shine through to illuminate the engravings. That's all 12 of the steppers in place and that layer completed. I paint this layer of MDF. It's only one piece of MDF I need, the second is just a spare. There'll be a total of 8 layers to this panel. We're looking at the first 5 of them here, the first of which here being the front fascia. The second layer is a 2mm clear sheet of acrylic. This is layer 3, a 6mm piece of MDF, spray painted black with countersunk holes, so layers 1 and 2 when removed will not require disassembly of layers 3, 4 and 5. This is layer 4, which is one of the key parts, because it's got the engraved text and lines of the actual gauges themselves. This is layer 5, which holds the 12 stepper motors in place but allows the transmission of light through to illuminate the text and lines. If we now start putting these layers together, if we look at layers 3, 4 and 5, we can see they form one unit on their own. Layers 1 and 2, they form their own unit, and the idea of this design is that if any time I want to alter any of the pointers. I only need to remove layers 1 and 2 away from it. I don't need to disassemble what is one whole unit. This is a completed instrument cluster. It just needs the pointers added. And this is layers 1 to 5. Layer 6 will be the backlighting. Layer 7 will be the easy driver boards. And the final layer 8 will be where the nanos are held. I take some time to look at the backlighting so that when the panel's finished, I'm happy that I'll have an even spread of light at the rear. Layer 7 holds the easy driver boards, which I found that the spacers actually act as a heatsink. I use small strips of electrical tape to just mark out temporary pointers whilst I was configuring them. And the actual pointers I used were just cut from the opal acrylic on the mill. I did spend some time considering whether to add some kind of reflective paint or almost glow-in-the-dark paint to the needles. But when I did some tests, if you look now, initially they really are quite bright when the lights are down, but they just fade so quickly. I just decided to stick with just the plain opal white. So that's all the key steps of the construction outlined. We can see it now running on IRQ serial, which is where the Arduinos are all connected via USB only. Before looking in part 2 of the extra footage at the conversion of this to an RS485 network, we'll just take a look now at the existing wiring at the rear of the panel, based on it being a USB connection only. Had this have been the final type of connection I'd have used for this panel, there'd be some extra layering just to tidy up all that wiring. Obviously not necessary given the adaptation we're just about to make. So in part 2 of the extra footage, we're now going to look at converting the engine instrument cluster to run over a RS485 network. So that'll be made up of a series of points to cover. The first one will be just to look broadly at RS485 communication and just have a bit of an overview of what that is. The second is to look at what are the fundamentals that have to be present within an RS485 network in terms of usage with DCS BIOS. The third will be to take the original Arduino sketches we had before and adapt them to run on an RS485 network. The fourth point will be to look at how we take the network fundamentals and put that into a design that we're then going to use, and I'll show the design that I've used in my network. The fifth point is then to cover the actual construction of the hub. And then the 6 points to look at installing slaves into the rear of the engine panel into what is layer 8. And finally we then look at the 7th point, which is to wire the remainder of the hub, now that we're satisfied that it works correctly in terms of all the gauges, and install that into the cabinet. So by cabinet, I'll refer to the data cabinet that I have, that is the overall one single big hub for the Simpit I'm building. So a few other points just to mention for this RS485 network that I've built. The first is that in building it, it's all been designed around and built at this stage purely for driving the stepper motors. That being basically to get this instrument cluster working. There's been no other real testing at this point for this network running other components that you may have within the Simpit. So it may be for it to run those other components, there may be other adjustments that may need to be made to this network. The other point would be that at different points in this video I may have referred to this network as an RS487, or could be referred to as a hub, or lots of other types of wording. Ultimately, the correct terminology is it's an RS485 network, which happens to run by using a MAX487 chip. In this second part of the video, we're looking at the conversion of this panel to run on an RS485 network. RS485 communication allows multiple devices to talk to one another just using a couple of wires. And in terms of DCS BIOS, what that means is that it would avoid needing to stream data to multiple Arduinos all sat on separate COM ports. So what this would mean is you just have one instance of a data stream to what would be a Arduino that would act as a master, and then via the wiring of the RS485 network, that would allow it to communicate to all the slaves. For someone just building a couple of panels, they might find that just a standard USB interface with each panel sitting on its own COM port would work just fine. But for someone looking to build a larger Simpit, this might be a method they want to look more closely at. So for RS485 communication, there's a number of different chips that could be used. The one I've used here is the MAX487 chip, which you can see in the middle of that table on the screen. And it's basically a low power transceiver which is for RS485 communication. And as you can see on that table, it has a reduced slew rate driver. So what that means is that particular chip is designed in such a way that it would look to reduce noise on that network. What we're looking at now is a breadboard view of an RS485 network in terms of the minimum required to create that network. So in this view, we can see that you have an Arduino Mega, and that will act as a master. And then you then have a series of slaves for which I've used Arduino Nanos. Now, the wiring amongst these is such that you will have a power supply coming in, which I've used a 12-volt supply, and that supply will branch out and power each of these Arduinos. So we can see that branches out and powers the master. It also branches out and powers each of these slaves. Now, with each Arduino powered, that in turn allows the Arduino board itself to run power into the MAX487 chips, and that's via the Arduino's 5-volt output. So it's 12 volts going into the Arduino boards and then 5 volts that they're supplying into the MAX487 chips. Now, each of those chips is interfaced into the Arduino board via 3 main connections. So if we zoom in and say have a look at the master and look at that MAX487 chip, and you see there's 4 designations here. Now, designations DE, ultimately are combined into one single input, which I've used as digital pin 2. And that's the case on the master, and also I've used digital pin 2 on all of the nanos as slaves. Then you've got outputs DI, RO from this chip, and they run round and feed into the TX, RX pins. And again, that's the case on the slaves too. But with the power lines powering the Arduinos and the chips, what that then enables is the chips via the data A, data B lines to communicate to one another. So based off what we've just said, if we just take a moment to slowly zoom in and move across this breadboard view, starting with the master, and just thinking through the power supply that comes into the board, which in turn powers the chip's interface from this side of the chip into the digital pin TXRX input to the board, and how that is effectively the same at the end of the slaves also. Power supply coming into the board, in turn the board powering the chip interface via the TXRX digital 2 pins to the Arduino board, and with that means of power distribution throughout the network, originating from the MAX487 at the master, communication through data lines A and B, which are interconnected from the master to all of the slaves. So the Arduino code for the sketches to make the master work and the slaves is very straightforward, and if we just have a look at that and bring it up on screen, we've got a basic Arduino sketch here with DCS BIOS fully installed on your computer. When you go into examples and you go to DCS BIOS, you've got an example of a master sketch and a slave sketch. So if we load up the master here, and you can see it's a very short, very straightforward sketch, and based on the pin input, the digital pin mentioned, you can see how that ties in with the line of code here for define textable pin 2. In terms of the slaves, again, if we go to examples, DCS BIOS, slave, we can see that you have a designation for which slave number it is, and again beyond that a definition of which textable pin. So it's standard amongst all of mine that I've used digital pin 2 for all of them. So the only real difference amongst the slaves is the slave number that I've allocated to that. So for the engine instruments, I've got 12 slaves, therefore numbered across 12 sketches, slaves 1 to 12. For whatever you panel-wise put onto the network, you need to put the code in relevant to that particular panel. So if it was a fuel panel, you'd put in snippets of code from the control reference library into this bit here. For me, I've used it for gauges. So I'll take the sketches that I had tweaked to make the engine instruments, the gauges, work correctly when I was running them all over IRQ serial, which is via USB ports directly, each gauge sitting on its own COM port, which is this sketch here. And then I need to adapt each of those 12 sketches, because it was one per gauge, into 12 sketches which will run on the new RS485 network. So really, when I take this sketch here, which contains all the information needed, the only real bit that I'm altering is I'm taking the IRQ serial line and removing it. If I bring up the new sketch to do a side-by-side comparison, you can see that in place of where you've got IRQ serial line, you have this in its place, and that is literally the only change. The code is exactly the same in all other respects. So when you're developing one of these networks, it does seem the easiest approach is to initially connect each Arduino directly via USB, tweak this code here to get it just right, get the gauge configured, and then when you're happy with that and you later convert it to an RS485 network, you remove this line here, and in its place you insert this block of text, and you just specify a slave number unique to that slave. So what we're looking at now is the final breadboard view of the setup that I've used for the RS485 network to connect and run my engine instrument panel. So if we zoom in here and have a look at this section, so everything that's on the screen now represents what will sit in the data cabinet, which basically is the hub. At this point here, we will have a patch panel, and a patch panel, it will have a number of Ethernet sockets, and each of those Ethernet sockets will be wired into the 4 main lines of the bus that we have here. So that bus is made up of the top rail being data A, which is coming out of the MAX487 chip allocated to the master. That runs in to this rail here. The second rail is for data B, which again comes out of that chip. And then the power supply we're going to use, when I set this up, this whole part of the hub will be sitting on a cantilever shelf, and the power supply will sit in the corner here to the right of the master. So therefore the 12 volt positive and negative will be wired to run round the side here and into these 2 rails, one dedicated for 12 volt positive and one for 12 volt negative. Now, in terms of the way other people may wire this up, it might well be that they would want to use a 4-core wire, and that's absolutely fine. To this point, I've pretty much standardised my wiring, that I've used Cat5, Cat6 Ethernet cables for everything, and they have 8 cores. So it could be that because they're 4 pairs of twisted wires, I could have each pair of twisted wires for each of these rails dedicated. But the way I've trialled here is that with those 8 cores, 3 of the cores will be wired into the 12 volt positive, 3 of them will be wired into the 12 volt negative, and 1 will be wired into data A and 1 into data B. So what that would mean is all of the wires within it are utilised, but in such a way that when I then wire up the slave at the other end, I'll have a good selection of the positive and negatives that feed in according on how I want to wire it up. And what that then leaves is the slaves. So in the case of the engine instrument, each slave, each nano will be for a particular gauge. Now, for some setups, I've seen people drive in more than one stepper with a nano, but I've decided that I will dedicate a nano per stepper. So if we look here, we know that ultimately we're going to have a total of 12 slaves to cover each of the gauges. And if we were, say, zooming in here, looking at this one, which would be for, say, gauge 1, as a slave, it's going to have an Ethernet cable which will plug in to this RJ45 socket here, and the 8 cores within the cable are going to come across and then feed into this connector here. So ultimately, I was looking to have another RJ45 socket at the other end, but I've not been able to get that into this design, perhaps something for the future. But the 8 cores feed into this connector, and then of those cores, the first one is one of the 12 volt negatives, which will run straight into the ground of the MAX487 chip. Then you've got data lines A and B, which feed straight into the necessary part of the chip. You've got one 12 volt positive which runs into power this slave, and in powering the slave it enables the slave in turn to, via its 5 volt output, to feed power into this chip. And then what you've then got is a number of other positives and grounds that are ultimately spare. So what I'll be doing for this is looking to connect all of this on a PCB. So it'll be the first PCB I've tried to do, put together when making my Simpit. I'll have a basic PCB that all of this will sit on, and some of these extra positive and negatives, they'll be used to be able to power the stepper, because that will need a 12 volt supply into the easy driver board. So to better visualize the wiring of the cable that connects these two together, if I bring up this view on screen here. Let's bring that back. This represents typical standard Type B wiring of an Ethernet cable, and we can see that this would plug into this socket here. So I've said that 3 wires will be 12 volt positive, 3 will be 12 volt negative, and then you'll have data lines A and B. So the way I'm going to utilise it will be these first 3 here will be 12 volt positive across stripy orange, orange, stripy green. The blue will be data A, stripy blue will be data B, and then these 3, green, stripy brown, brown, they will all be 12 volt negative. So what we've seen here then is a particular approach I've taken the first breadboard view of the fundamentals that you have to have in place and developing it to something that I think will work for me. There's no right or wrong. I suppose there's lots of different ways people might do this. They might just want 4 cores rather than 8. I know ideally if I do a revision of this, I'll standardise it with an Ethernet connection at either end. And as I say, I will attempt to do my first ever PCB as a platform for this to sit on to minimise all of the wiring and keep it in a nice small footprint. The first part of building the hub is to put the Arduino Mega onto a mounting plate, which can then attach to the cantilever shelf. And the same then happens with the MAX487 chip, which is plugged into a soldered IC 8-pin socket, so if there's any damage caused to the chip you can simply replace it. You can see at the back the one splodge of solder which puts the DE and RE pins into one. So partway through building the hub I want to run some initial tests to make sure that the mounted components then running into some slaves through a breadboard are working correctly. So I now need to create the distribution rails. So to do that I get a large piece of variable that I've cut to size, and then I solder up at the rear along the copper strips all of the pin headers which are protruding on the opposite side. Now if I just take a moment to flip that over, we can see the top 2, it's like a dual pin header, is for data A and B, and then the middle one is 12 volt positive and the bottom one's 12 volt negative. And for each of the 12 volt positive and negative I have split the rail so it runs across 2 each to spread the load. That variable with the distribution rails is then installed into the cantilever shelf, and we're ready to begin all the wiring now to take that into the patch panel. I do have plans down the line to perhaps redo the hub based on a PCB design which will significantly cut down on the wiring, but the wiring I have installed here works as needed, and as you can see I'm running some tests here to make sure that the 12 volt power supply is passing through correctly to the other end that will go into the slaves. I also take some time to make sure that data lines A and B are all working correctly and there's no cross connections between anything. With enough wiring put into the hub to cover the gauges of the instrument cluster, I can now start testing attaching slave devices. To keep the slave devices on a small footprint, I've designed here my first ever PCB. I did it in a free program called DipTrace. I say it's free up to a certain number of pins, so as long as the PCB is not particularly big, then it's something that you can use at no cost. So to the right there of the instrument panel, you can see one of them being trialled and tested. A little bit earlier in this video we looked at the breadboard view of the final design I used for the RS485 network, and it's basically that breadboard view of the slave and the wiring into it that I've just literally lifted that and put it onto a PCB design. So at this point I've soldered up all 12 of the slave PCBs and the nanos that will click into them, and got all the wiring ready to start connecting them. The whole idea of using these PCBs is to cut down on this sort of mess of wiring you can see here. So on the breadboard on the right you can see a whole load of wires feeding into an RS487 chip and back out then to the slave. So the idea is to move it into a nice, neat, small footprint, because there'll be 12 of these at the back of the panel. And then the wiring needs to be put in place to connect the easy driver boards to the PCBs. So that connects them from the point of view of the power feeding through to the easy driver that's needed, but also the information from the nano controlling the step and direction. And that's a slightly closer view of those PCBs. So I have to remove layer 8 to get back to layer 7 to be able to put all the wiring in place to then pop layer 8 back on top. So that's all of the wiring in place. All that's left to do now is to flash the sketches to the Arduino Nanos and then plug those into the PCBs and start a run of tests as I bring them all online. Before we now look to start powering this up, just take a minute to take a look at the back of layer 8 of this panel, and also the hub that it will be interfacing into. So I've initially wired up 1/4 of all of the potential outputs. There's 48 potential outputs. Obviously it was 12 I needed initially, but now that they're tested and in terms of the gauges I know that they definitely work, I can start to look to wire up all of the hub, so I know I've got all 48 slave outputs available. So I now spend some time very carefully wiring the whole thing up, but also making sure I run a whole series of tests to ensure that it all works as it should. So I can now take this hub and install it into my data cabinet. And we now have a quick view of this installed into the data cabinet. At this point the engine instrument cluster has been fully converted to run over an RS485 network. So as we power this unit up now, we'll see the initialization of the Arduino sketch, whereby the steppers move back a series of steps and they need to hit the end stop within that movement. So we now just open up one instance of a data stream, which will go straight through to the Arduino Mega, which acts as a master, and that in turn can cascade that data stream down to the slaves. So a good time to give some shout out. So first of all to FSFE and the developer of DCS BIOS and anyone else that's contributed towards it. Second of all to my father-in-law Phil for his usage of CNC machine, which has made a big difference to the aesthetic of my Simpit. And thirdly to ED Forum user Han Solo for all of his posts around RS485 networks, because this was the initial information I used to give me a good start and understanding to this. A few conclusions drawn whilst testing the RS485 network. The first would be that when that data stream is flowing from the master to the slaves, do not at that point unplug the cable, because disrupting that data flow will fry the MAX487 chip at the slave. A second conclusion is to definitely stick to using the MAX487 chip. I did trial for a while using the MAX1487 chip, but I did find that it ran extremely hot at the master, and also there was definitely some disruption of the signal to the slaves, and a drop out of that signal meant that there'd be times that the gauges would stutter, or they would temporarily almost lose their connection and be out of sync with the sim, or that the nano would reset itself and you'd suddenly randomly having some gauges starting off their initialization sequence. I can say that since using the MAX487 chip in all tests, and that has run for many hours now, this whole panel, all the gauges have run absolutely perfectly. One thing you'll notice in my designs is that I've not used a resistor at the ends of data lines A and B within the network, and there are bits of information both on the forums and the data sheets that say that that should be the case to be correctly terminated and to reduce noise. So if anyone is watching this that has quite a strong knowledge of these networks, it'd be interesting to get some comments from you in terms of, is it required to have a resistor, or would that just be the case if it was a 1487 network? And the fact that the 487 chip does work, is that because it has a reduced slew rate driver, and that in itself reduces noise to such a point that it doesn't need the resistors to terminate the ends of data lines A and B. Well, it's been a lot of fun to build this panel, and I hope that this video has been of some use to people watching, and hopefully some other people might go on to build a similar panel and to run it over this type of network. In terms of tools and resources to build something like this, I will put on my website mysimpit.co.uk downloadable Arduino code for one of the gauges. It will be gauge 12, the APU temperature, both if running over an RS485 network or not. And I'll also put on the breadboard views, which show the minimum requirements when using this network with DCS BIOS, but the final design I used for my Simpit. Thanks for watching.